Imagine living your life, every single moment, protected by this invisible, powerful force field. You can't see it, you can't hear it, you can't feel it.
Right.
But it's there, and it's deflecting all this lethal solar wind and deep space radiation. It's what makes life on Earth possible. We're talking about our magnetic field.
It is, and this is no exaggeration, arguably the single most critical planetary defense system we have. And for most of human history, we've just taken it for granted.
Exactly. But recent data, especially from satellites, is suggesting that the shield isn't just shifting, which, is natural, but it's weakening in very specific and frankly alarming ways. We're sort of moving the idea of a magnetic field collapse or a reversal from, I don't know, science fiction, into a subject of pretty urgent scientific concern.
And that's what we're doing today, a deep dive into the research around this planetary defense. Our mission is to synthesize the evidence, understand the mechanisms, and really detail, well, the chaos that would follow if the shield failed.
We'll start with the science of this weakening, then get right into the immediate disruption to our infrastructure, and finally, look at what it means for our health. Let's get into the state of our fading shield.
To really get the threat, you have to start with where the field comes from. It's generated deep inside the planet. Think of the churning molten iron of the outer core. It's a massive dynamic system.
A planetary scale dynamo, essentially.
That's the perfect term for it.
Yeah.
And its output is the magnetosphere, the shield that deflects charged particles from the sun, the solar wind, and also cosmic rays from, deep space.
So it's not just protecting us from space weather, it's a constant guard against everything.
Precisely. Now, about that weakness we've observed, the most tangible piece of evidence is a feature called the South Atlantic Anomaly, the SAA.
That's a great specific. We hear the term weakening, but what is the SAA?
Think of it as a huge growing dent in the shield. It stretches from South America across the Atlantic all the way towards Africa. Yeah. And in that region, the field's strength has dropped dramatically. It's up to 30% lower than in areas right next to it. Satellites that pass over it get bombarded with so much radiation.
I've read they have to shut down their instruments.
They do. They shut down sensitive electronics just to avoid damage. So this anomaly is, hard evidence that the core dynamics are changing right now. The shield is not uniform.
That makes the threat feel much more immediate. It's not some abstract global thing. Our satellites are already taking a beating in that specific spot.
Right.
But you mentioned the field changes naturally anyway, so what's the difference between this and just a normal planetary cycle?
That's a crucial point. The Earth's field does flip. We know this from paleomagnetic data. It's called a geomagnetic reversal.
North becomes south, south becomes north.
Yep, it's natural. The concern, however, is the speed of the transition.
How fast is fast?
Well, historically, a full reversal seems to take several thousand years. That gives life plenty of time to adapt. But the material we have now suggests a much more rapid scenario is possible.
And what happens during that flip?
It doesn't just cleanly flip over. It becomes chaotic. It can fragment into multiple poles and lose up to 90% of its total strength for, well, it could be for hundreds, maybe even 1,000 years.
So the key concern is that we could enter this weakened, chaotic state much faster than we thought.
That's the worry. And if that chaos begins, allowing all that radiation to penetrate our atmosphere, that brings us right to the most immediate threat, the complete collapse of our technological world.
What's terrifying is just how dependent we are on that silent protection.
Absolutely. The first thing that happens in a weak field environment is that charged particles, which are normally deflected, can suddenly penetrate deep into the atmosphere.
Yeah.
This causes ionization at much lower altitudes.
And that leads to systemic power and communication failures. The research points to a specific mechanism, right? Geomagnetically induced currents, GICs.
Exactly.
Okay, GICs. That sounds technical. Break that down. Why are they so destructive to our power grid?
Well, when you have these intense geomagnetic fluctuations, from a solar storm and in a weak field, for example, they create these massive, slow-moving electrical currents in the ground itself.
Okay.
These currents then look for the path of least resistance. And what is that? Long conductors, like buried pipelines, and most dangerously, the high-voltage transmission lines of our electrical grid.
So the power grid itself starts conducting this unwanted, overwhelming natural electricity.
Precisely. And the grid, especially the big transformers, they are not designed to handle these DC-like currents. The GICs can push them into saturation, they overheat, they can fuse, they can be destroyed.
And not just one.
Not just one. You can see them destroyed across huge regions simultaneously. This would lead to widespread long-term blackouts. And replacing these massive components, we're talking months, if not years, without power for major cities.
We even have a historical example of this, right? The Carrington event in 1859, and that was when the magnetic field was strong.
We do. That event was so powerful, it caused telegraph systems to fail, some even burst into flames. It shocked operators. But if an event of that magnitude hit us today, during a period of magnetic weakness,
The damage would be on a completely different scale.
exponentially greater, far beyond anything we've seen in modern history.
And that's just the infrastructure on the ground. Up in space, we'd face instant technological blindness. Satellites are the eyes and nerves of our global system.
Satellites are incredibly vulnerable, especially the ones in low Earth orbit, LEO. That's where most of our communication and weather satellites are.
Right.
Without the magnetosphere's protection, the increased radiation can just fry their electronics. Imagine losing our GPS network. That means immediate paralysis for transportation, logistics, agriculture, nearly all modern military ops.
It's so much more than a global internet outage. It's a loss of our civilization's real-time spatial awareness.
It is.
That paints a really vivid picture of technological paralysis. But the threat isn't just external. It translates directly to our biology, to our survival. What does all this radiation exposure mean for life on the ground?
If the shield collapses or stays weak for a long time, the risk becomes critical. We're talking about two main types of ionizing radiation: solar protons from the sun, and then galactic cosmic rays, or GCRs, from deep space.
And what's the specific mechanism of damage? How do they hurt us?
Well, both types of radiation have enough energy to directly damage human tissue, and more importantly, the DNA inside our cells.
So even though the atmosphere still protects us a bit.
It does, especially against the lower energy solar protons.
Hmm.
But the GCRs are extremely high energy. They're much harder to stop.
So this is a long-term threat. It's not instant, but it accumulates damage over time.
Exactly. Increased GCR exposure leads to a higher rate of cellular mutation, and that is directly linked to elevated risks for different cancers, for inherited genetic defects, especially if this weakened state lasts for generations.
And there's more, isn't there? The material also mentioned the ozone layer.
That's the other part of this. A weakened magnetosphere could also lead to a partial erosion of the ozone layer. That would compound the problem by letting more harmful UV radiation from the sun get to the surface.
So we'd be getting hit by high-energy radiation from deep space and more UV from our own sun at the same time.
It's a devastating synergy. And what's really important to understand is that this risk isn't spread evenly across the globe.
We're back to that geographical vulnerability you mentioned. You talked about the poles earlier. Why there?
Because the magnetic field lines naturally converge at the poles. They act like funnels,
Right.
Even when the field is strong, some radiation gets channeled down towards the Arctic and Antarctic. But if the field collapses or fragments, those funneling effects get amplified.
So people living at higher latitudes, say northern Canada, Scandinavia, Siberia,
They would face a significantly higher concentration of risk compared to anyone living closer to the equator.
it's a terrifying combination. A global tech breakdown while facing a biological threat that depends entirely on where you live.
Which really raises the final and most worrying question in the research. What happens if the Earth's internal weakness aligns perfectly with a powerful external event?
Right. This is the ultimate worst-case scenario, the catastrophic combination. Because if our own field weakening wasn't enough, we still have to worry about the biggest external threat. A major solar storm, a coronal mass ejection.
And we have to be clear, even when our shield is at full strength, a severe CME, which is basically a massive cloud of magnetized plasma shot from the sun, can cause huge disruptions. Carrington proved that.
But just imagine that incredible burst of energy hitting a shield that is already cracked. It's weakened by 30% in some places, and maybe it's actively fragmenting. That's the danger multiplier that moves this whole conversation from a serious disaster to something else.
An existential threat. That combination is precisely where the sources highlight the most severe risk. When the magnetic field is strong, it deflects most of the CME. But in a transition state, the sheer volume of charged particles that would get through it's just drastically increased.
So those GICs we talked about earlier, the grid killers, they become orders of magnitude stronger.
Correct. The technological damage from the solar storm gets amplified because our planet's natural defense is already compromised. So instead of, some minor blackouts, you could see a cascade failure across entire continental power grids.
The total grid collapse.
The long-term impact of that, combined with the elevated radiation exposure, It's almost impossible to fully mitigate without some truly radical preparation.
It's the perfect storm. Internal planetary physics meeting external solar violence. The sheer scale of that combined event, it really does push it beyond just a disaster scenario.
So if we just synthesize what we've discussed, the findings are pretty clear. The field is weakening. The evidence is the accelerating growth of the South Atlantic anomaly.
The risks are technological, rooted in those geomagnetically induced currents frying our infrastructure.
And they are biological, from galactic cosmic rays and solar protons damaging our DNA. And this isn't speculation. This is a factual concern from scientists studying the Earth's core.
And the message from the research is just as clear. Understanding this is crucial for future protection. Knowledge really is the first line of defense. It lets us adapt before we're forced to react to something we can't control.
That realization is powerful because we rely so completely on systems that assume this silent, invisible stability. It just shows a fundamental fragility in our advanced society.
So what does this all mean for you, the listener? We want to leave you with this final thought. Think about the last time you used a map on your phone, checked a precise weather forecast, or even just made a digital bank transaction.
All of those systems rely entirely on the silent, invisible stability of Earth's magnetic field.
We talk about climate change and earthquakes because we can see and feel them. But how quickly, in the middle of a global communication failure and technological chaos, would we realize that the very shield of our planet, that silent, indispensable defense, had fundamentally changed? It's a dependency we barely even acknowledge until it might be too late.